The edge of the observable universe has remained a mystery for many years, sparking curiosity and theories among researchers and enthusiasts alike. However, the James Webb Space Telescope holds the key to unlocking this astronomical secret. With its powerful lenses peering farther into space, it has already made a groundbreaking announcement about what lies at the edge of the observable universe. To understand this concept, it's important to first define the observable universe. This refers to everything we can see, measure, and detect from Earth or our space-based telescopes and experiments at any given time. It includes stars, galaxies, and other celestial objects within our observational reach. The observable universe is only a small part of the entire cosmos we cannot yet comprehend. While the full extent and shape of the universe remain unknown, the observable universe is estimated to span approximately 93 billion light-years. A light-year, the unit of distance in astronomy, represents the distance light travels in 1 year, about 5.88 trillion miles or 9.46 trillion kilometers. Therefore, the diameter of the observable universe is around 93 billion light-years, which corresponds to an unfathomably vast distance of about 5.468 quadrillion trillion miles. Around 13.8 billion years ago, the universe was born in a massive explosion known as the Big Bang. This violent event triggered rapid expansion, and ever since, the universe has continued to grow at an increasingly faster rate, driven by mysterious forces like dark energy. As the universe expanded, particles of matter began to cluster together under the influence of gravity, forming structures such as stars, galaxies, and eventually planets like Earth. Despite the vastness of the universe, it is predominantly empty. To put this into perspective, if we were to shrink our entire solar system to the size of a quarter, the closest star would still be about the length of 2 football fields away. And that's just within our own Milky Way galaxy, which is one of billions in the observable universe. The concept of the universe's edge is an awe-inspiring idea that has fascinated scientists, philosophers, and thinkers for centuries. While there are several theories about what lies beyond, the truth remains elusive. However, 3 primary hypotheses stand out. The universe is infinite. This idea is based on the cosmological principle, which states that the universe is isotropic, meaning it looks roughly the same in every direction. If this principle holds true, it implies that the universe continues expanding endlessly, without a definitive boundary. The universe is finite but without a clear edge. In this scenario, the universe is analogous to a giant sphere, and if you travel in any direction long enough, you would eventually return to your starting point, much like walking in a straight line on the surface of a sphere. The multiverse theory. This suggests that our universe is just one of many, each existing in its own bubble with distinct laws and properties. These universes may be completely separate from one another or could be interconnected in some way. The James Webb Space Telescope allows us to look back in time and explore objects from the early universe. Its advanced capabilities have enabled astronomers to peer into the universe's origins. A recent study published in Nature revealed that the telescope discovered 6 large galaxies that existed between 500–700 million years after the Big Bang. Researchers had expected to find small, newly formed galaxies, but the James Webb Space Telescope unexpectedly identified these much larger galaxies, challenging previous models of early universe development. These massive galaxies, dubbed universe breakers, have left scientists puzzling over their formation. Traditionally, we believed galaxies began as small clouds of stars and dust, gradually growing over time, but these discoveries have forced us to rethink our understanding of galaxy evolution. When the first high-resolution data from the telescope was released in July 2022, researchers were stunned. They questioned their initial interpretation of the data when they saw these galaxies appearing as large, pinpoint lights. By using spectroscopic techniques to analyze light across different wavelengths, scientists can gather critical information about these galaxies, including their composition, size, and distance from Earth. The mystery of what lies at the edge of the observable universe continues to captivate our imagination and fuel scientific exploration. The James Webb Space Telescope is poised to uncover even more secrets of the universe, pushing the boundaries of our understanding of the cosmos and our place within it. Its discoveries have already surpassed expectations, revealing surprises faster than anticipated. Some of the objects identified using Webb's data may not be galaxies at all, but could potentially be enormous black holes. It is now believed that the total mass of stars in the universe is far greater than previously thought, with estimates now suggesting it is several times larger than we once believed. This staggering discovery has shaken our understanding of cosmic matter, even though we have only explored part of the universe. In the meantime, using the powerful James Webb Space Telescope, an international team of space experts made another astonishing discovery. They found the oldest and most distant galaxies ever confirmed, dating back to when the universe was a fraction of its current age. Less than 400 million years after the Big Bang. The light from these galaxies traveled toward us over 13.4 billion years ago, as detected by the telescope. This discovery is comparable to early observations made by the Hubble Space Telescope. When the first images from the James Webb Space Telescope were captured, they revealed several potential galaxies. Through meticulous spectroscopic observations, astronomers have confirmed 4 of these objects, allowing them not only to study the properties of these galaxies but also to precisely determine their distances. To calculate a galaxy's distance, astronomers use a measurement called redshift, which is an indication of how much its light has stretched as the universe expands. Redshift estimates can be made from images taken through various filters, but spectroscopy provides the most accurate measurements, as it breaks down the object's light into its constituent wavelengths. The latest discoveries focus on 4 galaxies with redshifts greater than 10, suggesting they are extraordinarily far away. While the Hubble Space Telescope had previously observed 2 galaxies with confirmed redshifts of 10.38 and 11.58, the James Webb Space Telescope has captured even more distant galaxies, with redshifts of 13.20 and 12.63, revealing a time roughly 13.5 billion years ago, offering a glimpse into the early universe's history. Additionally, the James Webb Space Telescope's Deep Extragalactic Survey, called JWST, is a groundbreaking program dedicated to providing an unprecedented, in-depth view of the early universe. Launched in 2015, JWST was proposed by a consortium of instrument teams and has since been executed by over 80 astronomers and researchers from 10 different countries. This ambitious program has been allocated significant time on the James Webb Space Telescope to further our understanding of cosmic origins. The core mission of the James Webb Space Telescope, JWST, extends far beyond the confines of our planet, aiming to unravel the mysteries hidden within the vast expanse of space and time. One of its key objectives is to explore the distant regions of the universe, where light from ancient stars and galaxies has traveled billions of years to reach us. By capturing and analyzing this light with incredible precision, astronomers hope to uncover valuable insights about the universe's origins, the evolution of galaxies, and the development of celestial bodies over eons. At the heart of the telescope's advanced capabilities is its array of cutting-edge instruments, each designed to observe the universe across various wavelengths of light. The near-infrared camera, NIRCam, plays a crucial role in detecting the faint infrared signals emitted by distant galaxies and star-forming regions. This ability allows astronomers to peer through vast dust clouds that obscure visible light, revealing previously hidden phenomena. Complementing NIRCam is the near-infrared spectrograph, NIRSpec, which disperses the light from celestial objects into its component frequencies. Spectroscopy is vital for understanding the composition, temperature, and velocity of stars and galaxies, providing essential information about the physical properties and evolutionary stages of astronomical objects. Another essential instrument on Webb is the mid-infrared instrument, MIRI, which extends the telescope's observational capabilities into longer infrared wavelengths. MIRI is particularly important for studying the thermal emissions of exoplanets, brown dwarfs, and dusty disks around young stars where new planets may be forming. Its sensitivity to mid-infrared radiation enables astronomers to investigate a range of planetary systems and the conditions that might support life. Beyond its scientific instruments, Webb is equipped with a massive primary mirror, measuring 6.5 meters in diameter. This mirror is coated with a thin layer of gold to enhance its reflectivity in the infrared range where Webb operates. The mirror's large size and precise curvature enable the telescope to collect more light and achieve higher resolution images than its predecessor, the Hubble Space Telescope. Webb's position in space is strategically chosen to optimize its observational abilities. Unlike Hubble, which orbits Earth, Webb orbits the Sun at a location known as the second Lagrange point, L2. This position ensures a stable orbit relative to Earth, allowing the telescope to maintain a constant view of deep space without interference from Earth's atmosphere or heat radiation. The journey to launch Webb was not without its challenges and delays, but its successful deployment marked a remarkable achievement in international collaboration for space exploration. Led by NASA, in partnership with the European Space Agency (ESA) and the Canadian Space Agency (CSA, the development and launch of this state-of-the-art observatory involved the contributions of thousands of scientists, engineers, and technicians from around the world. One of the most anticipated capabilities of Webb is its potential to detect and characterize exoplanets, planets orbiting stars beyond our solar system. While Hubble provided the first indirect evidence of exoplanets by observing the dimming of starlight as planets passed in front of their parent stars, Webb aims to directly image these distant worlds. By studying the infrared light reflected by exoplanets, astronomers can analyze their atmospheres for signs of water vapor, carbon dioxide, and other molecules that could indicate conditions suitable for life. The search for habitable exoplanets is not just a scientific pursuit. It represents a profound philosophical and existential inquiry into humanity's place in the universe. The discovery of even a single Earth-like planet orbiting a distant star would revolutionize our understanding of the prevalence of life beyond Earth and spark questions about the potential diversity of life forms across the cosmos. In addition to its role in exoplanet research, Webb is poised to shed light on the formation and evolution of galaxies throughout cosmic history. By observing galaxies at varying distances and ages, astronomers can recreate the timeline of cosmic assembly and examine the processes that drove their growth and transformation over billions of years. This research is crucial for testing theoretical models of universe formation and understanding the factors that shape the vast cosmic landscape. After extensive observation of a small region of the sky, including the Hubble Ultra Deep Field, the James Webb Space Telescope, JWST, made a groundbreaking discovery. By examining this area across 9 different infrared wavelengths, the JWST team identified nearly 100,000 distant galaxies, each billions of light-years away. Using the NIR spectrograph, the researchers gathered light from 250 faint galaxies during a 3-day observation period. This enabled them to analyze the gas and stars within these galaxies and accurately measure their redshift values. These measurements allow astronomers to determine the intrinsic brightness of the galaxies and estimate the number of stars they contain. This marks a significant step in understanding galaxy formation over time, even without direct observations of their early stages. Studying galaxies can be just as challenging as understanding the early life of stars, which profoundly affects the evolution of galaxies. The JWST, with its remarkable capabilities, is answering many questions about the universe, revolutionizing our understanding of galaxies, stars, planets, and other cosmic phenomena. Launched in December 2021, the JWST is expected to operate for at least 20 years. It is already surpassing the accomplishments of its predecessor, the Hubble Space Telescope. The telescope has captured the imagination of scientists and the public alike, sparking a surge of scientific enthusiasm worldwide. Researchers are eagerly analyzing the raw data, sharing stunning images, and gaining new insights. After a complex deployment process, the JWST stunned the world with its initial images in mid-July 2022, providing an unprecedented view of distant galaxies, nebulae, and other cosmic wonders. With its advanced infrared capabilities, the JWST allows us to study the most distant galaxies and peer back in time to the universe's earliest moments. Since becoming operational in late June 2022, the telescope's powerful instruments have revealed a multitude of previously unknown galaxies, older and farther than ever imagined. Its abilities also enable scientists to capture detailed light from celestial objects like exoplanets and young stars, revealing their compositions and tracking their movements across the cosmos. This wealth of data is already providing valuable insights into the atmospheres of planets located light-years away, offering clues about their potential habitability. Additionally, by analyzing faint traces of light from the universe's infancy, the JWST has possibly detected the oldest black hole ever observed. This colossal black hole, with a mass millions of times that of the Sun, resides at the center of a young galaxy that formed just 570 million years after the Big Bang. Thanks to the JWST's powerful cameras, capable of looking back to the universe's earliest moments, this discovery offers critical insights into the early formation of black holes and their rapid growth during the first billion years after the Big Bang. The origins and evolution of these massive objects remain one of the greatest mysteries in astrophysics. As we delve deeper into the cosmos, the JWST continues to serve as a beacon of human curiosity and ingenuity. Launched with high expectations in December 2021, the JWST represents the pinnacle of decades of technological advancements, offering a new era of exploration and discovery.